Welcome to The Explainer. Today we're diving into a fascinating new model that claims to solve one of the biggest, oldest problems in all of physics. And the key? Well, you're not going to believe this. It might be hidden inside something as simple as the number one.
You see, for nearly a century now, physics has had this massive problem. It feels like our two best descriptions of the universe are in an all-out war with each other. They just don't get along.
So, in one corner, you have the heavyweight champion, Einstein's general relativity. It's absolutely beautiful. It paints this sweeping, elegant picture of gravity, of the grand dance of planets and stars and entire galaxies. It's the physics of the very, very big. And in the other corner, you have quantum mechanics. This is the wild, bizarre world of the incredibly small, of atoms and particles, where things get fuzzy and probabilistic, and frankly, just plain weird. The problem is, their rulebooks are totally, fundamentally incompatible. It's like one is written in English and the other in a language from another dimension. So for decades, the holy grail has been to unite them, right? To create a single theory of quantum gravity. But every single time physicists try to stitch the math together, it just breaks. It completely falls apart, spitting out total nonsense, like infinite energies crammed into tiny little points in space. But what if everybody's been looking in the wrong place? What if the answer isn't some complicated new theory with a bunch of extra dimensions we can't see? What if it's a completely new model, a new way of looking at things that's built on a couple of really clever ideas? It all starts by rethinking what we call empty space. Forget empty space. The quantum vacuum isn't a void. It's the actual fabric of reality itself. You have to picture it as this bubbling, fizzing sea of energy, with tiny virtual particles constantly popping into and out of existence. And this isn't just a cool idea. We have real experiments that have confirmed this is actually happening. And here comes the really big idea. The model introduces something called the unit harmonic operator. Now, stay with me, because this is cool. It's basically a super clever way of writing the number one. Instead of just one, it expresses it as an infinite series of waves. It literally takes the plain old number one and teaches it how to speak the language of the quantum vacuum. So what do you do with this new, souped-up version of the number one? You plug it directly into Einstein's famous equations of general relativity. And just like that, you've built a mathematical bridge. All of a sudden, Einstein's world of gravity and galaxies can talk to the quantum world of particles and waves. Okay, that's a neat trick, but how on earth does that fix the century-old problem of those pesky infinities? Well, it turns out it reveals a hidden rule about the deep, deep connection between matter and the very vacuum it's sitting in. Let's walk through it. It happens in 4 pretty logical steps. First, you take a particle, like a proton, and you put it in space. Its very presence organizes that chaotic fizzing sea of virtual particles around it. It kind of brings order to the chaos in its immediate neighborhood. Second, for that proton to be stable, to not just fly apart or get crushed out of existence, it has to achieve a perfect balance. The energy density pushing out from the particle has to exactly equal the energy density of the vacuum pushing in. It's a fundamental condition for its very existence. Now, that point of perfect balance creates a natural physical speed limit for energy. Think of it like a universal red line that energy levels simply cannot cross. This model gives it a name, the quantum vacuum spectral limit, or QVSL for short. And here is the brilliant part. Remember that infinite sum of waves that made up our special number one? Well, that expansion gets cut off by that universal red line. All those waves with infinitely high energies, they're just not allowed to exist. The physics of the vacuum itself forbids them. And with that, poof, the infinities that have been plaguing physics for 100 years, they're gone. They just vanish. So solving the infinity problem is, well, it's huge. That's incredibly elegant. But elegance isn't enough in science. A model has to make predictions, testable predictions. And this is where things get really, really interesting. So using that physical energy cutoff, the QVSL, the model can actually calculate real-world properties of matter. For its first big test, it set out to calculate the exact size of a proton. Now that might sound simple, but figuring that out has actually been a notoriously difficult problem for physicists.
So what was the result? It's pretty stunning. The model's prediction for the proton's radius is an unbelievably close match to the very precise value measured by the SELECT's collaboration experiment. We are talking about an extraordinary level of agreement here. But the model doesn't stop at the tiny scale. This is the amazing part. It applies the exact same logic, the same physics, to the entire cosmos. Using the Milky Way galaxy as its yardstick, it predicts the Hubble constant, which is just the rate at which our whole universe is expanding. Now get this timeline. Back in 2008, the author published the model's prediction for the Hubble constant. Then, everyone waited. 5 years later, in 2013, the Planck satellite mission, one of the most powerful cosmology experiments ever built, released its official measurement. The model's prediction, made 5 years earlier, was 67.1. And the Planck satellite's actual measurement? 67.3. That is astonishingly accurate for a prediction made a priori, meaning it was published years before the experimental confirmation. That almost never happens. So let's just take a breath for a second. We have a single framework built on one core idea that is making jaw-droppingly accurate predictions at both the tiniest quantum scale and the grandest cosmic scale. So what does this all mean for the big picture? Well, it means this single model offers a potential path to resolving some of the biggest mysteries in all of science. It seems to explain why particles have a definite size. It offers a solution to the ongoing Hubble tension debate in cosmology, and it even points to an origin for dark energy. And what's really crucial here, what makes this approach stand out, is that unlike more speculative ideas like string theory, it's not just abstract math on a blackboard. It is fundamentally anchored in stuff we can actually measure, from the size of a proton right here on Earth to the expansion rate of the entire universe. And that leaves us with a truly provocative thought. What if the key to unifying the cosmos isn't some exotic new theory that's impossibly complex? What if the most elegant truths about our universe have been hiding in plain sight this whole time, inside a deeper understanding of the concepts we thought we already knew?